So far, we have not actually solved any second-order differential equations. Think of the simplest example you can come up with. Likely, your example will be of the form a times y double prime plus b times y prime plus c times y is equal to 0. Ja, dat is goed. Hi there. So far, we have not actually solved any second-order differential equations. Think of the simplest example you can come up with. Likely, your example will be of the form a times y double prime plus b times y prime plus c times y is equal to 0. Such an equation is called a homogeneous, linear, second-order differential equation with constant coefficients. This is because the coefficients a, b, and c not only do not depend on y, but they do not depend on x as well. That this equation is relatively simple does not mean that it is not interesting. In fact, many important applications involve differential equations of this form. You have seen such an example previously when we talked about the mass spring damper model. Moreover, we will see that the solutions behave very differently depending on the coefficients a, b, and c. To give you an idea, here you see some graphs of the possible solutions of this differential equation whenever a, b, and c are greater than or equal to 0. In the first case, we have that b is equal to 0, which corresponds to the undamped harmonic oscillation. The other three graphs all correspond to the case where b is bigger than 0 and are called the damped, the critically damped, and the overdamped harmonic oscillators, respectively. We will see that the shape of the solution is determined by whether the quantity b squared minus 4ac is negative, 0, or positive. For solutions of this equation, we take inspiration from its first-order counterpart, which takes the form a times y prime plus b times y is equal to 0. This equation is both separable and linear. You can use the techniques from either separable or linear systems to show that the solution to this differential equation is given by y of x equals c times e to the power minus b over a times x. We see now that our solution is an exponential function, which is fully determined by the coefficients of the original equation. This means that exponentials are the key functions to look at. Hence, we will try to find an exponential function as a solution for our second-order equation. In particular, we try a solution of the form y of x equals e to the power r times x. Such an educated guess about the shape of the solution is called an ansatz. In this case, y prime is given by r times e to the power rx, and y double prime is given by r squared times e to the power rx. Plugging this ansatz into our equation yields that a times r squared times e to the power rx plus b times r times e to the power rx plus c times e to the power rx is equal to 0. Since exponentials are, as you know, always non-zero, we can divide this entire equation by e to the power rx, which leaves us with a times r squared plus b times r plus c is equal to 0. This is a relatively simple quadratic equation in the variable r. In this setting, it is called the characteristic equation, although it's sometimes also called the auxiliary equation. As you know, three different situations can occur for a quadratic equation, depending on the value of the number d, which is b squared minus 4 times a times c. If d is bigger than 0, then we get two different roots. If b is equal to 0, then we get one root. And if d is less than 0, we get two complex roots. Each of these situations leads to a different type of solution to our original differential equation, so we will treat them separately. We're considering the second-order differential equation a times y double prime plus b times y prime plus c times y equals 0. We tried the solution y of x is e to the power rx, which gave the characteristic equation a times r squared plus b times r plus c equals 0. Let's look at the case where d, which is b squared minus 4ac, is bigger than 0. If a, b, and c are non-negative, this corresponds to the overdamped harmonic oscillator. This is actually the most straightforward of the three cases. The characteristic equation now has two different real roots. Let's call them R1 and R2. Since we tried a solution of the differential equation of the form e to the power rx, this means y1, which is e to the power r1x, and y2, which is e to the power r2x, are solutions of our differential equation. In fact, we are done now, as the general solution of our differential equation can be written as y of x equals c1 e to the power r1x plus c2 e to the power r2x. As a more concrete example, consider y double prime minus 2y prime minus 3y equals 0. The characteristic equation is r squared minus 2r minus 3, which factors as r minus 3 times r plus 1. If this is 0, then r1 is 3 and r2 is minus 1. So the general solution to our differential equation becomes y of x is c1 e to the power 3x plus c2 e to the power minus x. We're considering the second order differential equation a times y double prime plus b times y prime plus c times y equals 0. We tried the solution y of x is e to the power rx, which gave the characteristic equation a times r squared plus b times r plus c equals 0. Let's look at the case where d, which is b squared minus 4ac, is equal to 0. If a, b, and c are non-negative, this corresponds to the critically damped harmonic oscillator. Then the characteristic equation has only one root, which is minus b over 2a. Let's call this root r star. Certainly, y1 of x, which is e to the power r star x, is a solution to our differential equation. But what could another solution look like? For this, we need a trick. Consider y2 of x is x times y1 of x, which is x times e to the power r star x. Then we can compute y2 prime as y1 plus x times y1 prime. And y2 double prime is 2 times y1 prime plus x times y1 double prime, where we make extensive use of the product rule. Then we can plug this function y2 into our differential equation to obtain a times y2 double prime plus b times y2 prime plus c times y2 is equal to a times 2y1 prime plus x times y1 double prime plus b times y1 plus x times y1 prime plus c times x times y1. Grouping the terms with x together, we get x times a y1 double prime plus b y1 prime plus c y1, and the remaining terms then are plus 2 a y1 prime plus b y1, which equals x times 0 plus 2a y1 prime plus b y1, since y1 is a solution of our differential equation. Recall that y1 was e to the power r star x, and that r star was equal to minus b over 2a. Hence, 2a y1 prime plus b y1, the remaining term, is equal to 2a times minus b over 2a times e to the power r star x plus b times e to the power r star x, which is 0. Therefore, y2, as we chose it, is a solution to our differential equation. The general solution to our equation will now look like y of x is c1 times e to the power r star x plus c2 times x times e to the power r star x. As a more concrete example, consider y double prime minus 2y prime plus 1 equals 0. This equation has characteristic equation r squared plus 2r plus 1, which is r plus 1 squared. If this is 0, then r star will be minus 1. This means that the general solution in this case is y of x equals c1 e to the power minus x plus c2 times x times e to the power minus x. We're considering the second order differential equation a times y double prime plus b times y prime plus c times y equals 0. We tried the solution y of x is e to the power rx, which gave the characteristic equation a times r squared plus b times r plus c equals 0. Let's now look at the case where d, which is b squared minus 4ac, is less than 0. If a, b, and c are non-negative, this corresponds to either the undamped or the damped harmonic oscillator. In that case, the characteristic equation has two complex roots. Let's call them r is k plus or minus I times omega, where I is the imaginary unit. Since the solution we tried was y of x is e to the power rx, the solutions become y1 star of x, which is e to the power k plus I omega times x, which we can expand as e to the power kx times cosine omega x plus I sine omega x, and y2 star of x, which is e to the power k times cosine omega x minus I sine omega x. However, here we run into an issue, namely that these are not real solutions, which is what we are interested in. Can we somehow turn them into real solutions? Recall that if we have two solutions to a linear differential equation, then any linear combination of those solutions is a solution as well. Therefore, if we consider the function y1 of x as half times y1 star plus of x plus y2 star of x, then this can be written as e to the power kx times cosine omega x. This becomes a real solution to the differential equation. Similarly, if we consider y2 of x as 1 over 2i times 1 star of x plus minus y2 star of x, then we can simplify this to e to the power kx times sine of omega x, which is also a real solution. So our differential equation has the general solution y of x is c1 times e to the power kx times cosine omega x plus c2 times e to the power kx times sine of omega x. As a more concrete example, let's consider y double prime plus 2y prime plus 5y equals 0. The characteristic equation now becomes r squared plus 2r plus 5 equals 0, which has solutions r is minus 1 plus or minus 2i. So the solution to our original differential equation becomes y of x equals c1 times e to the power minus x times cosine of 2x plus c2 times e to the power minus x times sine of 2x.